So for those of you who are just now watching the screencast as it's coming out, lecture may be canceled tomorrow due to my throat, which you can probably hear is kind of, what would you call it? Froggy? Bad, right? Not good, at any rate. So we have that packed bed reactor. It was a simple reaction, A goes to B. And then we had defined a couple of other parameters for it previously. So I'll put these over here on the left. We're not really going to change any of these, it's just we're going to add to them. So the density of the bed, which I'm just going to start abbreviating as rho sub B. It's, I think when I first introduced density of bed, I said sometimes it's rho B, sometimes it's rho bed. Just depends on who's writing it and how many words they can say. So our density of the bed was 2 kilograms per liter. Our rate constant, we said that was an elementary reaction, and it's irreversible, so we're not going to change anything about that, was 0.1 per second. This should be consistent with what was in your notes if you look backwards a couple of days. There was 100 kilograms of catalyst in there, which, by the way, kilograms of catalyst, you can have an enormous amount of catalyst inside these reactors. It can easily approach the tons of catalyst, so thousands of kilograms. Don't worry if some on your project, as you're calculating the weight of catalyst, if it gets up into the thousands, that's normal. That's how big these things can get. We had also dealt with a pressure drop. We're going to keep the pressure drop for this problem. And we had a simplified form that just made life a little bit easier in terms of coding. This particular form would have come from either the Bernoulli equation or a simplified Ergun equation. You'll have to do something similar to that for all of your projects. And then the inlet volumetric flow rate was 1 liter per second. So the only thing that we're going to change, that's essentially the entire problem, I think, from last time. Only thing we're going to change is we're going to worry about energy now. Because we have multiple ways to put that jacket on there, we actually have 4 different types of energy balances we have to look at, and that's what we're going to spend all day looking at, is what are the similarities between these. In addition to this information that we have here, if we need to worry about energy balances, we need some extra information, which I'm going to now give you in the blue. So we have to know what's coming in. So it's going to come in at T0 and P0. And we're also going to know that A is coming in at 3 moles per second. And it's pure, so there's no B coming along for the ride. There's no inert, nothing like that. It's just A coming in. We will consider this gas phase. Let me double check that I actually considered this gas phase before you write that down. Yes, this is gas phase. Can anybody guess what line in my code I was looking for to tell me if it was gas phase or not? What? The V code, right? If there was a line in my code that said V is equal to V0 times F over F times P over P times T over T, that only happens for a gas phase reactor. So a lot of this doesn't change whether it's liquid or gas, except for that line. And then we will try to figure out what's coming out on the other side, of course. So this will be, some temperature, some pressure. Uh-oh. Did it hard lock? No. And then whatever the flow rates are coming out. We're not going to worry about conversion right now. If we needed conversion, we'll calculate FA and then get conversion afterwards. The types of reactors we're going to do are twofold. So there's either whenever you deal with an energy balance, you've kind of got 2 distinctions. You can either do an adiabatic reactor, in which case none of that energy comes out, it all just builds up in there, which I thought of a great trick question. Let's say that was adiabatic and exothermic. What's the temperature of the outside of the reactor? What is it? It's atmospheric, right? Whatever the temperature of the outside of the reactor is. It was just a clever trick question I thought of. If it's an adiabatic reactor, all that energy is still inside the reactor. So if you just put your hand on the side of an adiabatic reactor, you would not presumably get burned unless somebody had very bad insulation on there. That is not going to come up on an exam or anything. It was just one of those things that we think about as we're walking along to class. The new parameters that we have, because we are now worried about thermal effects, we have to know all of the heat capacities. To keep things somewhat straightforward, we're going to keep the two heat capacities equal. And we'll just call them around 45 joules per mole per Kelvin. Ballpark heat capacities, if you're ever worried about heat capacities for gases, typically like 10 to a couple hundred. If the molecule's really big, then the heat capacity is probably in the hundreds. If it's kind of an everyday molecule of small size, a few carbon atoms, a few hydrogen atoms, those heat capacities tend to be around, I don't know, 10 to 50, something like that. The enthalpy, as given to us, is at 298 K. That's Kelvin K, not the other K. And this is exothermic, so it'll be minus 30 kilojoules per mole. The activation energy for that rate constant is 10 kilojoules per mole. Ooh, why is it way over there? They're supposed to be lined up. There we go. So 10 kilojoules per mole. Because we have an activation energy, we also need to know at what temperature that K was given. Activation energies by themselves are unlike enthalpies in the sense that they are not given for a particular temperature. That activation energy is 10 kilojoules per mole everywhere, regardless of what the temperature is. However, this K would have needed to have been given to us for a particular temperature. So we're going to assume that the temperature this was given was 600 Kelvin. And then we kind of have a subset of other parameters that we may or may not need depending on whether or not we're solving an adiabatic reactor or a jacketed reactor. If it's an adiabatic reactor, then we're not really worried about anything more than this. We don't need to know what's happening in the jacket. If it's a jacketed reactor, we have to know how efficient it is, or I shouldn't say efficient, how effective it is at pulling that energy out. And the numbers that we need in order to do that are two. One of them is the uppercase U, so that is a U, not a V. And that's the overall heat transfer coefficient, which will always just be given to you as a number. If you want to know how to calculate that, either wait for or review your 101B notes. It's about 800 watts per meter squared per degree Kelvin. And then we also need to know that little a parameter. So A, remember, was defined in a particular way. It's the surface area of the cylinder divided by the volume of the cylinder. So we only have a single cylinder here, so this would just be the surface area of a cylinder divided by the volume of the cylinder. That will typically simplify to 4 over the diameter of the reactor. We don't have a special subscript for diameter of a reactor. It's just uppercase D. There is a subscript that goes along for a diameter of a particle, which is not this. The diameter of a particle is D sub P, but the diameter of a reactor is not special. It's just D. And so we're going to assume that this reactor is 10 centimeters in diameter. So what does that mean? That means if you got out a ruler and measured it from here to here, this would be 10 centimeters. And so if you work that math out, I converted the units already, just so that we don't have to worry about more units. For 40 inverse meters. If you're trying to get an idea why inverse meters is a weird looking unit, we don't encounter it every day, that's like saying you have this much volume per unit area as you go down the length of the reactor, which, by the way the units work out, are going to have weird looking units of inverse length. So it could be per foot, per meter, per centimeter, whatever you want. And so, like I said, we've got two options here, and we're going to solve this for two different cases. Actually, 4 different cases. The first is an adiabatic reactor. I'm not going to shout out what you all think when I say adiabatic, because you should be thinking of a particular variable. But we also have a jacketed reactor. And the jacketed reactor is the one that's going to cover 3 different cases. So one of these cases, and we went over, I think, all of these cases on Monday. One of them is a constant TA. So the jacket temperature of whatever it is that's flowing through there, if it's water or something like that, is constant. The other options are the other two that we had talked about. So one is coflow. If it's coflow, the TA coming in is still going to be equal to the same old TA. I will finish that parenthesis in a moment. And then the other one is a counterflow. And again, that one has the same requirement, which is whatever the TA in is the same TA that we would deal with for the constant jacketed temperature. Does that seem more dim than it used to be? Maybe we're losing our projector as well. What is the temperature that we're going to do, or we're going to use? This is some additional information that if you have a jacketed reactor, you generally need to know this. All of these temperatures would correspond to things you would have to be told, and they will all be 300 Kelvin. The challenge with something like that is what we had seen yesterday, the isothermal, or not isothermal, kind of isothermal, constant temperature jacketed reactor. That's not too bad. You don't have any extra differentials or anything like that. The coflow one's not bad because it just adds another differential to the system. It's the counterflow one that's tricky because when you're looking at a reactor like this, the temperature that you know for your coolant is the one that's over here if you have a counterflow. So if you have counterflow TA coming in, you know it at the other end of the reactor. And that's a problem because if we're going to solve our differential equations, we have to know where we start, not where we end. ODE 4.5 can't take a combination of points at the beginning and points at the end and make them match in the middle. We have to do that ourselves. ODE 4.5 cannot do it, however MATLAB can do it. It's just not a feature of ODE 4.5 itself. So that's where we're going to have the majority of our struggles is to figure out what's happening with counterflow. It's going to come up in your project too. The process that we're going to do here in about 10 minutes, you can use exactly that process on your project, or if you can see how to make MATLAB do what we're doing, make MATLAB do it. That's perfectly fine too. So what I'm going to hand out to everybody, I'm not going to give you the full set of code, so we've got more code to work on. It's a simplified set of code. Specifically, this bit of code is only the differential equations. So your job will be to figure out what order these differentials have to come in without seeing the rest of the structure. You'll have a pretty good idea of what order these have to go in. But they also use an element inside MATLAB that you may not use every day. I'm not going to describe what the syntax is, because if I tell you what the syntax is, you'll know about 8 of the lines on here, because it's just following the syntax of this. The word, or the key phrase that if you don't know what it is, you should probably look it up on your phone. It's called a switch expression. And so the way that this code is structured, it will use a switch expression to decide which of these elements that you need to calculate, depending on whether it's adiabatic, or it's jacketed, or it's coflow, or counterflow, whatever it is. So if you don't know the syntax of a switch expression, look that up while you're working on this, and I will give you a hint. When you're working on that code, so the first hint is count how many cases you have. If you don't know what a case is, again, check out the documentation for that real quick. Shouldn't take but a moment or two. It's very similar to a for loop if you've never used one of those before. So count how many cases you have, then count how many Q's you have, and finally count how many expressions of dTA dW you have. That will be a strong hint about how to structure that that switch expression, because there's going to be a pattern to those numbers. Again, I think I have about 60 of these, so I'm going to pass these around. We're going to take, we've got, what are we, 320, we've got till 350, we've got about 30 minutes. We'll take maybe 10, possibly 15 minutes. Just focus on trying to get, there's only differential equations here. Organize these in such a way that it seems logical, where if the rest of the code was added to it, you would be able to quickly decide whether or not I need a particular expression for adiabatic, a particular expression for constant TA, coflow, and common flow. The other differentials are on here too, so the material balance is on there. We don't actually have a pressure expression because this is, it's non-isobaric, but we have an explicit expression for P, so we don't need a differential for P. In your code for the project, you'll have one more element on here as differential of pressure with respect to W. So I'm going to pass these out. Feel free to work with anybody around you. And I will end up posting the actual code that we're about to use with some modifications, because there's some stuff to make it look pretty on the screen that you don't want to see. So you will eventually get the answers. I assume that's why we're calling it. It is screenable too, just like the other code, so obviously we'll have to work on the screenable. And rapidly running out too, so make sure if you're working with teams that you pass in answers on. We'll get some any extras up front that I can? We do have a couple extras if anybody wants one. Thank you. Oh, actually, we have a lot of extras if anybody wants one.